So this is just one topic, but it takes a little bit to explain. So we're going to calculate molality instead of molarity. And this is going to help us rank the boiling and freezing points of solutions. This is what we're going to do. So this is a colligative property. So when we change the boiling or freezing point of a solution, this is called a colligative property. And the definition of a colligative property is a property based on the number of solute particles. So the number of particles dissolved, not the identity of the solute. So this is dependent on just number of particles. Okay, if we have more particles, we'll have a greater effect. So it'll increase the boiling point more or decrease the freezing point more. If we have a pure solvent, that solvent has a lower boiling point and a higher freezing point than if we have a solution. And this is what the lab is about on Monday. So you're going to do fun things like boiling different things with and without solutes. So honestly, this lab is a little bit tedious, but it's about colligative properties. No, open my palette. Okay. So this picture is what I have in my head. So the dark lines are the original solvent, and then these dashed lines are when we add a solute. So we've made a solution. So originally, the solvent we usually think about is water. Water boils at 100 degrees Celsius, and it freezes at 0 degrees Celsius. When we create a solution, let's go back. When we create a solution, the freezing point is depressed. We drop the freezing point, okay? And when we add a solute, we increase the boiling point. So this is the picture that's in my head. Both of the boiling point is increased, the freezing point is decreased. So we're just increasing the liquid zone when we add a solute to our solvent. Okay, so that's how I remember the boiling point is elevated, the freezing point is depressed. And then depending on the number of particles in solution, if we have more particles, we will have a greater effect on the freezing point depression or the boiling point elevation. Okay, so again, this freezing point elevation, boiling point, freezing point depression, boiling point elevation depends on how many particles we add. So we need to look at the compound that we are given in Alex, and we have to decide how many particles are going to be given by that compound. So if we add 1 mole of sodium chloride, the sodium chloride is going to break into its ions. So we get sodium ions in solution, and we get chlorine ions in solution. So remember we talked about modeling our ions in solution. So when this breaks apart, for every 1 mole of sodium chloride I add, I actually get out 2 particles. So this is going to have a greater effect than something that only adds 1 particle for 1 mole. Okay? Calcium chloride has an even greater effect on the freezing and boiling point because we add 3 particles. We get calcium 2+, and we get 2 chlorine minuses. So more particles in solution, greater effect on boiling and freezing point. Okay, so looking at this next one, magnesium chloride, how many particles does that give us? How many? 3, good. We get Mg2+, and we get 2 Cl minuses. How about KBr, how many particles do we get? 2, good. So we need to recognize that because when we do the problem, we're going to have to multiply by the number of particles we make. Okay, if it is a covalent compound, then it's going to only give us 1 particle. So if there's no metals, then it will always give us 1 particle. Okay. There's one exception. The exception we talked about was acids and bases. Did you guys all get the list of acids and bases? Okay. So bases are pretty easy to recognize because bases always have a metal. But acids, they will have the hydrogen at the beginning. And also in this Alex topic, it will say this kind of acid, and then I'll give you this formula. So if it says acid, then that's going to break into more than 1 particle, like an ionic compound. So that's where the acids show up on this problem that we're going to do together. So watch for that. Okay. All right, the other way we can think about the effect on the freezing and boiling point is the size of the molecule. If it's a small molecule, it's going to have a greater effect. If it's a large molecule, it's going to have a smaller effect. So that means it's going to change the boiling point. Elevation is not going to increase the boiling point as much. It won't decrease the freezing point as much if it's a larger molecule. So it's like inverse. So if we're just comparing 2 molecules that both give 1 mole of particles for 1 mole of compound, then the larger one will have a smaller effect. So sometimes you don't even have to do the math for this problem. If you have like all compounds that don't dissociate, then you can just look and see which one's bigger. That one's going to have the smallest effect. But we're going to go through and look at how to do this with math. So the best way to do this problem is using the molality. So we take the total moles of solute. So if it's ionic, like sodium chloride, we're going to take the moles of sodium chloride and we're going to multiply it by 2 because we actually get 2 moles of particles out. And then we divide by the mass of the solution. And then the highest total molality will have the greatest effect. So the biggest molality will drop the freezing point the most. It will also raise the boiling point the most. And this will make more sense when we do an example. You should always go through and do mark the water first. Trying to find my pen tool. There it is. So this is really important. You should go through and do the water first. And now it's going to turn off again. Okay, so every time water is going to have the highest freezing point. Every time water is going to have the lowest boiling point. So I expect every time you do this question, you get the water part right. That's 25% of this question. Okay, you're ranking 4 solutions based on their freezing and boiling point. Water has the highest freezing point. It has the lowest boiling point. And then if you add a solution, it increases the boiling point, it decreases the freezing point. So go through, do water. First, mark water. Water has the highest freezing point, it has the lowest boiling point. So on the test, I expect everyone to get at least 25% on this question. Okay. Are you ready? We need a minute. We're good? Okay. Okay, we're not going to do this example. We're going to do one and out, and it should be all right. Okay, so you're going to get a table like this. It says like the same thing up here every time. And then we get the same mass of different substances added every time. And it's going to tell me. So this one's called glycerin. This one's called potassium hydroxide. This is an ionic compound. It's also a base. Ionic compounds will dissociate, bases will dissociate. So we get 2 particles from this. This is potassium nitrate. This will split up into potassium and nitrate. If it says acid, something, if this could be, if there was a hydrogen here, then this is called nitric acid. It will say nitric acid. It will do the same thing. It will split into 2 pieces. Okay, so watch out. If it says acid, it's going to break into its hydrogens and ions. Okay, also notice we have the same amount of water in each situation. So we're just like doing an experiment. We're controlling for how much water, and we're changing the mass. Okay, so every time we should always do water first. So what did we say? Water should be what? Highest. Good. I don't know why my first box doesn't have the probably list yet. Okay. And then water should have the what boiling point? Lowest. Okay, so we've got 25% of our question done. Okay. Every time you should get that one right. Alright, so now we need to find the molality so that we can compare them. We're gonna rank the molality. So I'm gonna do this on the board over here. So I'm gonna do the first one. We have 3.5 grams of glycerin. We have C3H8O3. And I need the molality. So this is the number of moles of particles divided by the kilograms of solution. Okay, so, all right, we have 300, let's do this first. We have 300 milliliters of water. We need this to be in kilograms. If we look right here, it tells us the density. So the water density is, for every 1 milliliter, we have 1 gram, right? That's right. Okay. So then milliliters cancel, it's just 1 to 1. So for 300 milliliters, I have 300 grams of water. Okay. All right, so this is the water part of the solution, but we also have this mass. So let's go ahead and add those together. So this is 303.5 grams. Technically, we would just get no decimal places because this has no decimal places. Yeah. And this is this many grams of solution. Okay, but we need this in kilograms. Kilograms of solution. And that's going to be the same for all of them except water. Water will have 0 as our molality. Okay, so we need this part now. We need the number of moles. So this one, we're going to do 3.5 grams. We need to convert to moles of particles. So how do we get from grams to moles? Good. Divide by the molar mass. Good. For 1 mole. So I'm going to use the Alex calculator to do this because it has the. Oops. I can't use that on my board. It has this calculator. Oh, it's because it's too big. Okay. It has a periodic table. Oh, someone also told me if you click on this button, it has some of the molar masses already. So we're going to do that. We're going to use those. Okay. So we have, I just learned this yesterday. So we have 3.5, and we're going to divide by the molar mass, and it's given us it's given us 2. I don't know why it doesn't give us 3. That's dumb. Divide by this one. Okay, that's the number of moles. And then we need to check, is this an ionic compound? Are you going to get, is this going to dissociate? Are you going to get ions? No ions. This is, it's called glycerin. This one will not dissociate. So the number of moles that we add is the number of moles of particles. Okay. So what did we have? 0.03. Let's do this over. 8. Okay, and that's moles. All right, and then we're going to divide by the kilograms of solution. And this will be our molality. So what I like to do is I like to have a table. Water's molality is 0. And then when I do this part, divide by 0.3035 equals 0.0125. Okay, that's my molality for the number 1. And this would be moles per kilogram. Okay, so we're looking for the biggest molality that will have the greatest effect on our boiling points. All right, so let's go ahead and do the next one. So we have 3.5 grams of what is it? KOH? Yeah. KOH. So again, we're going to divide by the molar mass, whatever this is, for 1 mole. And they gave this one to us also. Again, I don't know why they didn't give us all 3. That's kind of dumb. So we're just going to type in 3.5 divided by, oops, I didn't type it in. 3.5 divided by the molar mass of KOH. Okay, so that is 0.6238. This is moles.
Oh, this one was 0. It's 0.0.
Oh, thank you. Okay. All right, so looking at this compound, if we add 1 mole of this, how many particles are we going to get out? Is this going to dissociate? Yes. We're going to get out K plus and OH minus. This is 2 particles. So I need to multiply this by 2 particles. So this is moles. This is moles of particles. My conversion factor is moles of particles per mole of thing that I added. Okay, if you're gonna keep track of your units like that, or you can just think there's 2 moles, so I need to multiply by 2. Okay. All right, so I'm gonna do that. I'm gonna multiply by 2, and then we need to divide by the same molality or the same mass of solution. Okay. Divide by the mass of solution. 0.3035. Okay, so this molality, number 2, is 0.411 moles per kilogram. Okay, questions so far? Are we doing okay? Okay, so then we need to rank the last ones. So the last one is 3.5 moles of KNO3. I'm going to multiply by the molar mass. I don't know why they didn't give us this one. So we'll do this one by ourselves. Okay, so 3.5 divided by, and then I'm going to pull up this periodic table. We have a potassium. Where is potassium? I forgot. There it is. And then, excuse me, we're going to add a nitrogen. And then we're going to add 3 times oxygen. Okay, let me make sure that looks right before I type it. Okay, that looks right. So then this is my number of moles. Moles. And then is this going to dissociate? Is this ionic? Is it an acid? Yeah, good. We're going to break into this K plus ion and this NO3 ion. So what do we need to multiply this by? 2. Good. 2. Let's put a 2. Okay, so I need to multiply by 2. And then I need to divide by the mass of solution. Okay, and then this is my molality for solution number 3. 0.2281 moles per kilogram. This is 0 moles per kilogram. Okay, so then we need to rank these in order. So like this one is the biggest number. So this is going to have the greatest effect on the boiling point and the freezing point. So let's get rid of this. So we know water is going to have the highest freezing point. So this is how I think of this. We have water. This is our boiling. This is our freezing point. If it has a bigger molality, this one will be what is it? Lowest, yeah. 1 will be lowest freezing point. This has the greatest effect. So lowest freezing point will have the largest molality. Okay. And then number 1 will also have the largest boiling point for the solution. Oops, and I think they call it the highest. Highest, and this will also have the largest molality. Okay, does that make sense? So biggest number is going to have the greatest effect, and then we just rank them. So number 2 has the greatest effect. So we're going to say that one is the lowest freezing point because it has the greatest effect. It's going to have the highest boiling point. Everything okay? Does that make sense? Okay, what one will be number 2? Which one will have the second lowest freezing point, the second largest number?
KNO3.
Okay, and that's this one, right? Yeah, good. KNO3. 2. And then this one must be 3. It has the smallest molality. It's going to be the closest to the freezing temperature and boiling temperature of water. Okay, and then which one is going to have the next greatest difference, or next, yeah. So this one had the greatest change in boiling point. Which one's going to have the next greatest change in boiling point? Yeah, KNO3, good. And if you get 1 and you're pretty confident, you can just reorder them. Okay, let's check. Okay, all right, good. Okay, questions on that? Does that kind of make sense how to do that problem? All right, there will be one of these on the test. Sometimes acids come up, so make sure that you're confident in answering this question.